application of error correcting codes in free space optical communication में we are looking at error correcting codes. This is coding scheme that aims at detecting and correcting errors. If we look at some of the coding schemes, what they will do is they will start using more and more information to predict what was the received signal, uh, and how much similar was it to the sent signal. This is some reference for the standard errors that you will receive in telecommunications technology. So these are the number of errors for different systems. So this means in a billion bits transmitted, you will have one error. So that's standard range. It can extend up to this also for a very good system design. I put all the references so that I do not violate any others image rights or any other uh, work. My goals are the work I'm doing. My goals are to increase the data rate, reduce the errors, reduce the usage of energy consumption should be low. I want to pack in as many as data bits I can pack into the available bandwidth. Then I need to have a very fast transmission. Communication has to be very quick, and the cost and complexity of implementation and should be less. So some of them are conflicting goals, and which some of them are to be minimized. Limitations are technical. Nyquist says there has to be some bandwidth requirement with a given message signal, otherwise, it will be received in error. Then there is the famous Shannon Hartley channel capacity theorem that limits the usage of bandwidth, and a certain amount of rate can be um, achieved on a channel to transmit your signals. There are technological limitations. Hardware implementations are always limited by the technology that we have at the moment. In LDPC codes, they were long back invented by Gallagher during his thesis at MIT, but due to lack of sufficient electronics, they were not practical to implement and then make use of. And then there are your own personal requirements to be fulfilled. You are going for 1 kilometer range or more than 1 kilometer range, then that will limit your system implementation. The measures that we will do to test the quality is bit error rate versus SNR graph and then coding gain. Recently, this news came in which 16 million kilometers away, which is 40 times the distance over the moon, infrared laser was has successfully transmitted data. So this news has come up on 23rd November 23. Anyway, coming back to the basic digital communication system, I will be working on channel encoding and decoding, then modulation and channel. So first working on the error implementation, error correcting schemes. I'm trying to reduce the error probability for at a given expense of bandwidth or decoder complexity. Signal modeling can be done using random variables because messages come from a sample of messages and can be turned up in random expected by the system. So is the noise. Then we can model them with Gaussian random variable and a Gaussian PDF, because central limit theorem says that if there are many different noise processes occurring together, they sum up and tend to be Gaussian. The thermal noise cannot be removed from a system, so it has to be included when you are designing a system. You have to include its effect, and it is referred to as white noise because at all frequencies its power is constant. And since they are uncorrelated, the white noise at different samples, the system becomes memoryless, and we are having editing white Gaussian noise nature. There are other noise also, but this is the one which we will use to simulate, implement, or our system. So modeling is done like this. The received signal is sum up with noise due to channel, and we are excluding the impulse response of the channel also does something to the signal, but that we are saying that we have an ideal distortionless channel. So we keep our analysis simple. We could simplify the EWGN channel by a binary symmetric channel. We can do it. In books we have seen this model being used to have present some problems. Figure of merit is signal to noise ratio. Average signal power is suited to analog signals, but for digital signals that are limited in time, energy is more fitting figure of merit. So average power and signal energy in signals and systems concept adapt to this digital communication. So we use suppose let us cut the signal theory, come back to the point. The point that I'm trying to make is that if there are m bits, if there is a symbol m generated by some bits, then that symbol is given energy. That energy will be divided into bits used. So the energy per bit is this. Energy can be represented by power into time, and power can be represented by energy upon time. Now classic signal to average signal power to noise power is written like this. If we start substituting average values, uh, the noise that we are considering, and it is time limited, and the average noise power, we move around a bit and then we reach EV by N naught. So this is also unitless as this was, and this is what we are going to use in our simulations for digital communication. A small example, that if we have BPSK transmission, that is the data rate will be 1 bit per symbol, sorry, 1 bit per second, yes, 1 bit per symbol also. And if you use QPSK, 2 bits per symbol will be sent, and QPSK will use half the bandwidth to transmit the same data which BPSK will take. So band spectral efficiency is achieved by QPSK, but for long distance inter-symbol interference, errors will cause QPSK to fail. So BPSK has nice spread signals which will reach further distance than QPSK modulated signals. Now, these modulated signals become analog at antenna, and they are represented by, we'll see later. Here, this small picture, I want to emphasize that if the bit time of this signal is smaller, then the more number of signals can be sent, and it will demand more frequency. So higher frequency equates to higher data rate. Now talking about noise variance, how noise will be put into our digital system. We will add noise using the model that we are using, AWGN additive wide Gaussian noise. The variance is given by N naught by 2. Variance is actually average power of a signal. So statistics and our systems technical information match up like this. Again, not going into the theory, how if you want to think about it, it can be done like this. There is this error floor where noise is coming, then there will be some more noise at times, and sometimes it will be lower. It happens on both the sides, so the signal will be something like this. So this is the mean, and these are the deviations. We'll find the deviations by subtracting the deviations from the mean and squaring them so that we have numbers, and the average of these numbers will give you variance as in statistical theory. But since we have squared it, we are no longer in the units of the the system we were talking about, so we square root this variance and we get standard deviation. But here we are looking at voltage square is proportional to power, and that is why variance and power are same. So this is average noise power in sense, and average noise power, spectral density of white noise gives us average power. Power spectral density of white noise can be found by uh, taking autocorrelation of, which is just correlation of shifted function. So that gives you its Fourier transform will give you its results. Fourier transform will give you noise spectral density. So rather than going into the theory again, let us continue. And here what I want to do is use this and substitute in our previous derivation that we have seen here. So SNR is EB by N naught. In this we want to substitute value of N naught, and we will rearrange and get sigma square noise, average noise power. So let us keep this. I want to fix this and save it, and let us continue. So this will be our average noise power, and I will add this to my digital signal. Metrics of performance that I will use is waterfall curves. So bit error rate versus SNR. Why do we use log plot? Because it shows large range, so we will be able to see huge data sizes and then the errors involved, and it also helps us to see the coding gain. So that's why not linear, we do it in log scale. So this was a simple example to show difference between log scale and linear scale and usability of the log scale. Then I have two types of modulation. Not modulation, I am trying to um, find the bit error rate. So I'll do a Monte Carlo simulation, or I can use the complementary error function to find the bit error rate. So complementary error function can be used to find the bit error rate, and in the book Todd K. Moon on page 21 one can find how. So this is the reference in this on page 20 and 21. How do we end up with this formula to find bit error rate? It is complementary error function. It is equivalent to Q function, and how Q function is used to probabilistically estimate that the received signal has, there is an optimum threshold in the Gaussian distribution. So there will be two signals, A, centered at A, another centered at B. Suppose this is representing 0 and this is representing 1. So what is the probability that the received signal R lies in this region and it crosses this threshold value? So if the received random variable has crossed this side, probability of error will be given by the probability of error of this bit and probability of error of this bit. So to show this, I have saved that part which is here. So in the book it is explained in detail again, and then in NPTEL lecture also the same explanation is given. So our work here is to focus on implementing the system using this formula. Then other one is Monte Carlo simulation. I will generate some bits using randi function and then count the total bits sent and add some noise to it and calculate the error probability. We start with the MATLAB simulations with a very low end PC, and first simulation is finding probability of error using a complementary error function which has independent variable SNR. If we keep increasing SNR, the errors will fall. This is what this graph is showing. So when the SNR is minus 4 decibel, there is one error in every 10 bits. When SNR increases, errors reduce down. So if you send a billion bits at 11 dB, you will expect only one error to happen. Now this is a MATLAB code that has been used to generate this graph, and I have taken a snapshot of the database also. When this code is run, then you will have these values stored, and this BER is calculated using complementary error function formula. It is you will not appreciate this at present because we have not understood how error complementary error function is giving the bit error rate, but the reference will help you appreciate this slide. Next, the same thing is doable, achievable in Excel, Microsoft Excel, or Excel kind softwares, because they have these spreadsheet softwares have inbuilt mathematical formulas that can be accessed and used. You just type in one value and then stretch it down, you will get the values, and then you can plot a graph. It can be validated by references from books or online lectures. So this is one of my viewings on web. So this is Neptel course by IIT professor Professor, it should be removed, Professor Andrew Thangraj. And we for move towards Monte Carlo simulation, in which I will generate messages. The data rate will be 1 bit per symbol, and the code rate is 1. That means I am not putting any FEC encoding scheme here. We will do modulation, which is BPSK modulation, and the bits will be converted to waveforms, and I will represent them with +1 and -1. These waveforms will be transmitted through the channel and received. Hard decision detection will happen. So input bits will be sent generated using a random generator, and modulated data will be sent in channel so that it survives the channel and reaches the receiver as per the requirements of the channel. Modulation is done. Since we are doing wireless communication, I start with BPSK modulation, and then at receiver hard decision detection is done. S hat is there because we don't know if the received signal is exact match of the sent signal, that's why a hat is there. But these two should be same. This is what is expected from this system. So if we send a 0, it will be modulated as 1. We are representing a 0 with +1, and the noise will degrade it somewhat, and then it will be detected back as 1 because it is positive. So positive means it must have been 1, and then decoded back to the message, which is +1 represents a 0 bit. So this is our decoded bit. Now what happened here is that 0 was input data, it was BPSK modulated. 0 was BPSK modulated to +1, and then the noise killed it so much that it drove it to the negative side. And due to this signal is detected as, since it is negative, the receiver thinks that it is a negative signal, and negative means negative one for binary transmission, and negative one is converted back to message which represents 1. So this is an incorrect interpretation of the transmitted message. So this is an error due to heavy noise that corrupted the signal. Now, sometimes the noise is more, sometimes the noise is less correctable. Too much noise cannot be corrected, and the detection system fails. Now let us implement this using MATLAB. This is the MATLAB code I have used. I have sent 10 to power 7 bits for a 1 SNR, sending them in loops because MATLAB and the computer system cannot crunch huge numbers. The system will not process faster. So to make it process faster, I will send this 10 to power 7 bits in chunks and then add up the errors that I will receive. So I am sending the message of n block bits, and 0 or 1 will be generated. Just one of these two will be generated randomly, and the size will be n is 10,000 bits at a time. And then I will transmit this after modulating. This is code for BPSK modulation. Again, this code converts 0 to plus 1 and 1 to minus 1. And this was referenced from books as well as the Nattel lecture by Professor Andrew Thangraj. It's a neat way to BPSK modulate in just one line, so I have used it. And as sir has taught and I have taken the course, I have liberty to use it here with proper suitable referencing. And further, I have written this received message. Now the received message must have traveled in air, and I have added the noise to it. I have added the noise power. Noise power is variance. So sigma is standard deviation multiplied by a random number generated from Gaussian distribution. So this multiplied with our sigma, we calculate our sigma based on the formula that we showed before, and as per the SNR, the sigma value will increase. So if our SNR is very small, then sigma will be very large, ending up with huge number of errors. So in every 10 bits, one error will be there when sigma, our noise, sorry, our signal is 0 decibels. And after adding noise to the signal, it is received and hard detection is done. All the bits that are negative, after adding noise, they will change their value a bit, but all those are negative, they will be counted as 1, and all those are positive are zeros. They are understood as zeros. Errors will be calculated by matching the message generated vectors with the received vector. When they are not equal, the total number of errors are added up, and they keep getting added up when the loop progresses to complete its 10 to power 7 block length. So this block runs for it runs 1,000 times. Every time 10,000 bits will be crunched and errors will be added on. So when this loop finishes, we'll have 10 to power 7 bits sent on 0 dB level, and the total errors will be counted. And this small code I have attached to capture errors and show you the database in live that errors are happening. And there will be a error vector somewhere. There it is. I will generate a error vector which will at each decibel store the total errors happened in the block, total block of bits sent. So this is the snapshot of the database in which when the energy was 0 dB, there it is, 5,63,227 errors were captured. And as SNR increased, since with iterations I am increasing the SNR from 0 dB to 12 dB, here it is, and it is calculating the variance. So each time the variance will be changed and errors will be calculated after completion of 10 to power 7 bits, and those errors will be divided by total block length. So BER will be given. So this is these are the errors, and bit error rates are not, I have not shown the database, but simply it is the amount of errors captured. Here it is divided by total bits sent. So I am dividing 10 to power 7 here, and the errors that I am counting and adding will be in the numerator. So after generating this database, I sketch this plot, and this plot is showing that the previous simulation of complementary error functions prediction of bit error rate, it is same, and my Monte Carlo simulation is giving the same result, except here there is a little difference. This little difference means there is some change of SNR. SNR allows more SNR, lesser errors. So SNR is a key, plays a key role here to reduce errors. And at larger SNRs, the errors are totally killed to zero, no errors happen. So if we increase the block length, we'll be able to see errors. That is what the understanding is. And if we change the transmitter power, this graph will shift here and there. So let us first uh, emphasize on the current simulation, do it multiple times and see if there is some other things happening. And if we notice that when we increase the SNR, the graph starts to detach a bit from the theoretical graph. Our Monte Carlo simulations are a bit different. So having a note of this, we move further and increase the code length from 10 to power 7 to 10 to power 9, and we start seeing errors at higher SNR also. At higher energy of transmission, we still note some errors are now being observed. So this means that more bits need more power to be transmitted. So more transmitter power, increase the transmitter power, you will reduce the errors. So more transmitted bits possible, increase the number of bits, you will increase the errors. And at higher SNR, errors are now showing. And why this curve is not overlapping? This is because I did a small mistake here. Here I wrote this code, part of line in the code is wrong. I should delete it. I have actually deleted it and rerun the simulations. Why I deleted it? Because theoretical plot starts from 0 dB and my Monte Carlo simulations plot will start from 1 dB. So it is already giving some extra energy. That's why lesser errors are being shown. So I have corrected this just by deleting this and keeping the SNR somewhere here. It should be written. That I must have done in the corrected code. So there I have removed it and I have set the SNR to change from rather lower than 0 dB to show that yes, it then creates more errors. If lesser energy is sent, is given to the transmitted bits, then more errors will be resulted. If you see at 8 decibels, less errors are happening compared to the Monte Carlo simulations. So this is the correction and understanding of SNR producing errors. Now, this is the reasoning for sending block bits rather than sending 10 to power send bits altogether, because the RAM starts being heavily used, and you'll slow down your system, and uh, it's not a good state to be in. So for fast simulations, what you can do is you can send them in blocks. So then you can also use parallel computing toolbox, but we'll use it when we need. This was the small code that I inserted to see where the errors are happening, because errors are happening in random. So we need to see that randomly where the errors are happening. To see that, I captured the message and the received message block, then compared it where they are not equal and summed them up. So I found 64 errors. To see those 64 errors, I added them or to addition, or I just simply XORed them to result in ones when there is dissimilarity between the message and the received message. So these ones highlighted, this is at the eighth number and the 8th bit is in error. So the one that was transmitted was actually received as a 0 in the 8th bit. Now again, studying about the SNR, when the SNR is very low at this block size, these many errors happen, but when SNR is increased, the at this block size, no error is reported. So let us increase the block size and see if we can get an error at 13 dB also. So I increased to 10 to power 8 from 10 to power 7, still no error. Then I increased to 10 to power 10, and then I found so many errors started coming up. That means that we can we can see that we need energy to send bits. More the bits, more energy is needed. We validate our simulations, our Monte Carlo simulation and the theoretical simulation with the book reference. Again, I am using following Professor Andrew Thangraj sir's lectures, NAPTEL lectures, titled LDPC 5G standard, something like that. I have taken this course, and then I don't remember if I have given exams. I've already given 8 to 9 exams, NAPTEL exams, and they are very useful. So I would recommend other learners also to enroll into them if you have time. Then coding loss simulation is being done. At this point, I will see that what happens if I implement a forward error control scheme that adds redundant bits or parity bits to check up on the errors and make predictions or make corrections. But we will not see the decoding, but we will first investigate that what coding will result into. Coding will have more redundant bits, and those redundant bits will consume the transmitter power, and thus there will be more errors. So what I'm trying to say here is that after channel encoder, when you have added the parity bits, redundant bits, then they will use up the transmitter power and bring down the SNR. That essentially bringing down the SNR will create more errors because there is not enough power for the bits now, because the power is now shared between bits. So let us say this is the rate, the code rate. It was 1 before. We were not appending any bits to the message bits to ensure their correctness. But when we are adding, then we say, suppose for one bit we are sending two bits, one as guard bit and the message bit, then the energy is spread into those two bits. So this will decrease and the probability of error will increase. So at detector we will notice that. Let us do that. Let us implement this code for different code rates. And when I implement for different code rates, that means for one message now I'm sending 2 bits. Why? One bit is guard bit. For one message I'm sending 3 bits. 2 bits will be guard bit and one message itself. So these are FEC schemes which have these code rates. The more the guard bits, the more the parity check bits, the good error correction scheme it is. And we have to pay for the bandwidth, but and maybe we need to pay for the decoding implementation at the receiver, but this provides us with error free solution. Now without encoding we have this curve, and at say 6 dB SNR, the errors that are happening is in every 10,000 bit one error is expected. But when we send extra bit, the energy is shared among the 2 bits. Then at the same time, the loss of energy makes it susceptible to more errors. So more errors in just 1,000 bits rather than 10,000. Now in just 1,000 bit you will see an error. And this simulation is trying to tell you that if you will increase the bits, the transmitter power is held constant. If it is held constant, then the transmitter power will be shared amongst the bits and it will degrade the performance. Now this degradation has to be compensated at the receiver. The FEC scheme actually aims to do that. Not all FEC schemes can come back from the loss and then provide extra coding gain, which is the feature of the coding scheme. Our realization is that we need to keep this initial loss due to adding redundancy as low as possible. That is why in the books they say that coding scheme is good if it is quite close to the rate 1. So near 1 rate codes are they must have been very efficient codes to correct errors. So we are moving left so that we can use less SNR. Long distance communication will be achievable because with less SNR, if we can transmit the data successfully, then it is a good communication system. So FSC scheme needs to first bridge the gap that it has created due to addition of redundancy. Then it has to perform during the decoding, which we have not done till now. We are holding it. We are at the detection stage of the the transmitted FEC signal. So we have to move further. Now implement the FEC scheme. Let's start with the simple repetition code. In repetition code, we have just one bit. It is repeated more times so that we ensure that this is reached as sent. Errors will strike and it will change the 1 bit or 2 bit. If we are lucky, only one bit is changed, then with majority rule, we will be able to tell that it was a 0 that was sent. So this is the message and this is the code word. One bit is represented 3 times each. So it is strengthened its presence. It has strengthened its presence. And if noise affects here and there, we have the majority bit still holding to tell what was its nature. So if this is the channel offers only 1 bit errors, then we can essentially correct the error and come back to the message that was sent. 1 bit errors are correctable by majority decision rule. 2 bit errors, if they happen, they will they cannot be corrected, but there is some error that has been detected because code words are only 000 and 111. So if they corrupt in two places, they will end up in an invalid code sequence, and we know that there are error, but we cannot know that what was the bit that was set originally. Actually, two errors will make us forced to believe that it was this was a 1, which is not the case. So 2-bit errors cannot be corrected. Then 3-bit errors will actually go undetected. It has got 33% efficiency only, and if we keep increasing the parity bits, the efficiency will worsen. So that is the drawback. The minimum distance tells us how strong the code is. So if this is the code word, if we change one bit, it will go to 001 or 010 or 100. These all these invalid codes, and the valid code, they form a sphere of its sanctity, that it is 000. If one bit error happens, that it is 2 bit away from the other code, so one bit can flip back to the original message, and you can tell that this is the message that was sent. So T is the error correction capability, this distance, the minimum, and let us skip all this. And this is the way how. Now this is a very good online resource by Eigen Chris on his channel, and he explained how d minimum comes up to be 2t plus 1. If you have minimum distance 1, 0 errors detected and corrected. If you have 2 distance, then 1 error and all that. And you see the series that is happening, and then convert it into formula and rearrange it and get this. So it is self-explanatory. Rather than me explaining, I would want you to see this web page or visit the Eigenchrist channel, and there is this beautiful explanation of this formula, how it comes up. All this has been taken from his site. So this is bounded distance decoding, the way of decoding that we are seeing, finding the original message, that word that was sent, and efficiency and all that we learned. Now let us implement the coding scheme in MATLAB. Again the same block diagram, and here is where I will implement, and here is where I will decode. So this is how I will do. I will generate a message randomly. So the message is, suppose in example 1, the code word will be repeating this 3 times. So this is the code word, message is 1, repeated 3 times, this becomes code word. In MATLAB it is done like this. Then BPSK modulation with 1 is represented by -1. It can be done with this, thanks to Professor Andrew Thangraj sir. And then channel noise will be added. This is the average noise power generated by standard deviation times the random noise from Gaussian distribution with the mean 0, variance 1. So it gives noise to our message signal. 1 is represented by -1 in BPSK modulation, and this is the noise. What do we do with this? We receive this. We receive this and demodulate it using hard detection and soft detection. Hard detection will see majority. What is there? Majority -1 is there. -1 represents a 1. So these are ones, and we decode it as 1. And soft decision decoding sums it all up and sees if it is negative. It is negative, then it is 1. If it is positive, it is 0. Let us take an example to understand this. Suppose we receive this vector. This is received, repetition of the message 3 times. Now how do we say what was sent, a 0 or a 1? First, what we will do, in hard detection we'll see two positives means two zeros are there, and one negative, one is there. So 100 is the detection, and two zeros means the majority, means that it was a 0. So majority rules tells with hard detection that 0 was sent. And the other scheme of decoding, soft decoding, is that we'll sum this up. If we sum this up, we receive a negative number. Negative number is -1. BPSK modulation, -1 represents that we had a 1 in the transmission. Repetition code has been implemented in MATLAB, and I have generated this sketch. Now repetition code is not good enough in providing a coding gain. What coding gain is actually, okay, from this graph I will try to explain. This blue line, this continuous line shows the uncoded. These circles, these dashed lines, these are showing our these two are showing our decoding stage, and this dots, these line, this line is at the detector, the coding loss that happened, during transmission and reception. And then after decoding, the repetition code could make up only for the coding loss it created due to addition of redundancy, so it is not useful. We are not improving upon the theoretical uncoded message that we are sending. We are not improving upon them. We have not achieved a better bit error rate at a SNR, or at a bit error rate. We have not created a less SNR signal. So what we want to do is we want to move on to the Hemming code, or the next code that we are going to look at, which will actually make up for the coding loss as well as provide some coding gain. So it will first add some redundancy. After coding, it will add some redundancy, and it will move the spread the energy amongst the redundant bits, and will create more lesser SNR, will create more errors. But when decoding will happen, it will start making predictions, and then it will bring back here. So that's what we want to see, and it will happen with Hamming codes. Hamming codes general definition. This is, we have a block of bits. It's a block code. We append parity bits, appending parity bits, and we can generate H matrices. This should sum up to 0, and arranging these equations, we have 7 4 Hamming code 2 to our 7 total, total 2 to power 7 128 total code words. On the valid code result will be the 4 message bit. 2 to power 4 will have 16, so 16 code words will be the valid code words. Others will create a space around the valid code words with a d minimum to have capability of error correction. So I have made a H matrix, and I could make a G matrix, and then I have checked the validity of G matrix also. There are many ways you can make H matrix. It is taking longer, so I will just explain what has been done rather than explaining each and everything. So if we swap the dummy variables, you can make another H matrix. And here, this is a book reference, and this is what I have done. It does not match, so I have swapped the columns Q and P, and then now these highlighted ones are valid code word. These are matching my code word. These Hamming codes can be viewed on Ncube, can be projected on 2 dimension, but it becomes too much for a computer to crunch. And this is a very small code length, and the complex figure has grown too much. What happens if we go for the current standards of code lengths over 50 to 4000? So our computers will fail at this. This is syndrome recording, in which 7 are errors and all 0 represents a correct transmission. This is the theory part. I don't want to go into. This is my simulation part. This is how it has worked, and this is the result. And there has been a significant coding gain achieved. So continuing with the explanation, trial 1 gives us this. Trial 2 with small block length gives us faster results in 6 seconds. So coding gain is soft decision is more, and in hard decision it is same as uncoded. 15,11 Hamming code has 4 redundant bits, so better performance is there. Comparing the repetition and having repetition codes of decision is same as uncoded, so repetition code is not a good code to implement for error correction. Hard decision of repetition code is even worse. Having code hard decision is good, soft decision is even better. It takes some amount of time to crunch out the numbers and all that. We move to LDPC code. LDPC code theory I am skipping. I am using Gallagher's method and then one more cyclic shift method to generate sparse matrices. Sparse matrices are generated with these conditions. The two ones have to be in two columns and one row once only, and then making these matrices and then stacking them. we can make a sparse matrix. So I've written this code and I'm making using Galar's method and following these conditions, and these is the matrix in which any two columns will have two ones in one row only once, and then we will permute them and stack as many as number of ones we need in a column, so making regular LDPC code. Now the permutations are limited, so the size of this is limited. That's why we need to increase the code length so that we can get a better distance, minimum distance feature and error correction capability. I further written the code and I could make these. So I have obeyed the rule of two column pairs having one, and this is one sparse matrix. Having made the sparse matrix, I have generated some samples. These are the sparse matrices generated by my code, MATLAB code. Then I have made generated generator matrix by another online reference on YouTube. Sir Kumurthy Raju has a video on YouTube. He explains that if we have this equation and we write its entrants, we rewrite them with the parity coefficients and have this solution uh, validated by S2 H1 inverse, and S2 inverse is actually parity bits. So parity bits I is G, we make G. So using this we can make G. So I, from the from the sparse matrices that I have made, I can make the G matrix, assuming that this is a H matrix. H matrix need to be linearly independent, so I have used a MATLAB function to find the rank using Gaussian elimination. We have removed mm, the equations or the rows that are not linearly independent. Otherwise, two rows of H matrix, if they are in dual space, that means that if the linear combination of two results in third, then this is not a different parity equation, it is same parity equation, so it is not useful. After making H and then G, I have generated a received signal according to same PPSK modulation and adding noise. At 1 dB I'm having 2 3 noisy messages, and at 10 dB not having a message. With this construct I can start decoding with bit flip algorithm. This is the explanation of bit flip algorithm, how it works. In general, it uses the received bits and the H matrix and multiplies them and sees where the problems are generating some rows. If this is number, then it will detect. So what it does, it just checks for one bit position. Errors don't die out, so it's not useful. Trying to make it find multiple errors, but that does not happen. For 2 bits and 1 bit it does perform okay, but for higher number of errors it does not do well. So we go to bit flip belief propagation algorithm. In that we have done some simulations in which we are achieving coding gain, and this is the size. Now the H matrix plays an important role. The distance property of the matrix helps us find more errors. So rather than this small block length, I have increased the block length, and more parity bits are now there to check on the errors, and we have increased the coding gain. So hopefully from the low end PC I'll move to a high end PC and then find a better curve somewhere here. That is the aim. And then according to the system I will draw using channel capacity available, the achievable rate and error, and the channel limit graph. Comparing all the codes done till now, we see the performance. So let us see this. These triangles are LDPC codes, some product algorithm. These squares are Hamming codes, soft decision. These lines, this continuous line is theoretical, and this dot line is Hamming hard detection. These circles are soft repetition codes. These dashed lines are hard repetition code. So it takes some time to find answers, and this is where we are heading, and this is the graph that we are intending to reach to. Thank you for this and listening on about this. This is another experiment that I did. Now I'm going practical rather than simulating. I have an Arduino Uno board and then a small cell, a toy laser guns, laser pulled out, which is having this specifications. I have referenced it from online. Professor Harold did this long ago and was felicitated in some university, and there's a YouTube video in which he was able to achieve 7 megabits per second data rate. Receiver is solar panel, transmitter is some laser, and at a short distance. I did the same. I This is the setup that I have. I have my Arduino Uno board. This is the laser transmitter. This is the solar cell, and this is this light will fall like this. I have written a small code with the help of my Manan. He is my partner in not crime in this small project work. And this Arduino board we bought for about 2000 rupees, was it? Yeah, I have a dream that we don't the students don't need not buy all these things, but we want these things in our possession, our control, to make the projects in our own time. This was done, I think, late in the night when everybody is sleeping. Are at our full concentration and we can do what we want to do with the kit we have, the equipment we have. So what we are doing here is we are transmitting light from Arduino board. The light is transmitting through the laser connected to the pins of Arduino board. Arduino board is programmed to send bits. Those bits will turn the light on off. You cannot see the light being switched on or off because it is at very fast rate. And when we increase this distance or decrease this distance, the voltage level increases and decreases. So with the varying these varying readings are with varying light intensities as the distance is changed. So this is the snapshot of that. And this light, the laser that is received on the solar cell, this light doesn't seem to flicker. It is just constant light, but it is flickering, which is captured on the Arduino interface on PC. So we sent 800 bits per second in 25 seconds, and data rate 320 bits per second was achieved. Now, having discussed this, my sir saw this, and I told me that the solar cells are designed to have they are designed for achieving power rather than the responsivity feature. Diodes should be used to can be used to can be used and compared the change in data rate. So we'll investigate more on this later. This is the code that I used and some calculations that I did, which I don't want to discuss at present. Feeling sleepy because I have just finished with my presentations, and now I am putting this lecture together so that I may remember next time when I pick this up again. Happy New Year to people who are watching this at the time, near time I am making this. And if anybody has any questions, you can write in the comments. Thank you. This is error correcting codes application on the free space optical transmission system.